Last time we saw how to create the geometry and mesh in Salome. In this part, I'm going to show you how to set up the simulation in CodeSaturn, and then we will take a look at the results in Paravis. In the terminal, we start by creating new CodeSaturn case. Once it's created, we get 3 folders. One called data to store the parameters of the study, one called resu where the results will be stored, and one called src where you can put your own C++ codes. We copy the mesh file we exported from Salome into the mesh folder. Once that's done, we can open our project in CodeSaturn Gate. As you can see, the name of our case appears along with the 3 folders we just mentioned. Now, inside the mesh section, we upload the MED file. Once it's loaded, we change the execution mode to mesh processing only, and then we run the computation. This step only takes few seconds to complete. Once the mesh is processed, we switch the execution mode back to standard computation. Then we go to boundary zones section and import the preprocessor log. This will automatically display all the boundary zones. At this point, I recommend renaming each zone clearly. That way, it will be easier to identify them later when setting up the boundary conditions. Next, in the flow model section, I selected atmospheric flow. I kept it with constant density inside the atmospheric flow settings. In this section, I'm configuring the atmospheric model. Either import a Meteor file or idealize the data manually. In my case, I went with the second option. For the roughness length and reference height, I used values from Eurocode category 2, which corresponds to a typical suburban terrain. The wind speed is set to 27 and the direction is 270, meaning the wind enters from the west. This orientation was chosen to ensure consistency with the domain setup, where the inlet is defined along the x-axis. The latitude and longitude are used internally by CodeSaturn to calculate the sun's position, which is important when simulating solar radiation or daylight cycles. Values like temperature and pressure are left at their default settings. After that, I activated gravity along the z-axis with the value of minus 9.81, which is required for the atmospheric cases. If you leave it at 0, the simulation won't run. For the turbulence model, I selected the standard K-epsilon model and kept the default volt function. Then, in the physical properties section, I choose air as the material. For the dynamic viscosity, I manually entered a value of 1.8 epsilon minus 5. Now, moving into the boundary conditions in this window, we can see all the boundary zones we renamed earlier, each one showing its assigned nature. For the bottom surface, I selected the smooth wall. For the inlet, I activated automatic options, so the inlet type is chosen based on the atmospheric data, and I did the same thing for the outlet. The sky boundary is set as symmetry. For the structure, I also applied the smooth wall. Finally, the remaining boundaries that we grouped under symmetry are set as symmetry as well. For the time setting, I went with the constant option and selected the sampling algorithm. I also set the reference time step to 0.1 and the number of time steps to 200. In the numerical parameters section, I left most of the setting at their default values. The only change I made was in the solver setting. I set the pressure solver precision to 1 epsilon minus 5. Everything else was kept as default. For the post-processing settings, I set the output frequency to every 10 time steps. In the results writer section, I use the same value. Don't forget to activate the option to output results at the start of the calculation. It is important to have that initial state. In the monitoring section, I added a single probe with coordinates at 50 along X and 0 along Y and Z, which allows us to track the velocity or pressure evolution at that point. Also, I selected the point CSV as the output trauma for easier analysis later on. In the Service Solutions Control section, make sure to activate both normal and tangential stress options. This is important because it allows us to visualize the pressure effects around the structure in the post-processing step. Finally, we can run the simulation. Just click Run and the simulation will start. Once the simulation is finished, we can move on to the post-processing and start visualizing the results directly in Salome Paravis. In Salome, import the 3 result files we need for visualization. For the fluid domain, I will display it as an outline just to keep the focus on the structure. Then, on the bottom boundary, I select normal stress and do the same for the structure. I will go ahead and hide it to keep the view clean. In filters, we will choose the option Cell Data to Point Data in order to smoothen the color discontinuities caused by the mesh discretization. Then we will modify the colors. We will also filter the results fluid domain. I will choose Stream Tracer so I can see the movement of the pressure or the velocity along the structure, with a resolution of 500 and pressure as a result. Right behind the building, the characteristics eddies typical of turbulent flows are clearly visible. If we now focus our attention on the house, there is a red face corresponding to a maximum of the pressure color map. This is physically making sense, as the wind is along the plus X direction and is therefore applying a consequent pressure on that face. Displaying the streamline along this plan and setting their color with the pressure color map allows to also observe some pressure diffusion effect along the y-axis. Indeed, we still see the maximum of pressure in the side of the house facing the wind and the pressure area behind, but we see the non-zero pressure areas are not exactly before or after the house along the x-axis. Pressure is slightly diffused on the sides. If we now color these lines with the velocity magnitude, we can clearly confirm a minimum of the velocity after the wind encountered the house. This is consistent, as it means the house has effectively blocked the wind. We could have used the glyph representation like this to get analogous information. In conclusion, Code-Saturn atmospheric module can be used to simulate more realistic wind profile rather than imposing an ordinary inlet. This can turn very useful in areas such as a wind protection in cities like in this video, or in environmental studies. Please note that this video has a pedagogical purpose. If you are considering to use Code-Saturn for studying the effect of wind, make sure to gather real-world data as much as possible to properly parameterize your study and, if possible, have some data to confront the results of the runs before changing the wind profiles. Feel free to contact the Simvia team if you need help with your modelization. That brings us to the end of the video. I hope it was helpful. If you found it useful, feel free to like, comment, and subscribe. And if you have any questions, drop them below.